So this is your question, right? How Oscar will know these DIs? Like,
Yes.
but Oscar, suppose we are looking for alpha 5. So Oscar knows alpha 5 is nothing but this alpha up to, yeah, alpha 5 is beta 1 XOR beta 4. This Oscar knows, right? Because Oscar knows the LFSR. LFSR is public.
Yes, sir.
So in that way, Oscar will be knowing that what is alpha 6. Alpha 6 is the XOR with these 3. So like that, Oscar has to simulate that part, okay? If it is alpha 2021, 2021, something like that, so Oscar knows the LFSR, so Oscar can get these DIs.
Sir, Oscar have to calculate the keys, means the beta i's, beta 1, beta
No,
2,
no, no,
all this.
beta is, they are unknown. That is the main part. If
Yes,
Oscar
sir.
knows
That is,
beta,
yes, sir. That is unknown. So he want to calculate that using
he
the
wants to
alpha.
calculate that.
Yes, sir. Using alpha is. So now we have some linear equation like he
But
knows the alpha is.
your question was how this coefficient will come. This
Yes, sir.
coefficient Oscar can simulate because Oscar has the LFSR. LFSR connection is known. So like how Oscar will get alpha 5? We just need the coefficient di. So for alpha 5, di is d1 is 1, d2 is 0, like this, because Oscar knows the connection. That's why Oscar, even though these are unknown, Oscar knows this will be the equation.
Okay, sir. It's fine now.
Thank you.
Okay. Thank you.
Oscar is having the LFSR, so Oscar can do the simulation part. Good. So we move to the this thing, block cipher again. Is this lecture slide is visible? So after this block cipher, we'll start the modes of operation. I thought to finish the AES first, then we'll move to the modes of operation, because some example of modes of operation we'll see some image input. So those are done on AES. So better to. Okay. So full screen. Is this visible to you?
Yes, sir.
Thank you. So, okay, so like we have discussed the attack on DES. DES was broke completely by the this Electronics Founder Foundation, even with the help of exhaustive search attack with the parallel computing. If we have they have designed a chip where they can each of these processor can do the one DES encryption or decryption, and then there are many processors are around, and then that was done in 1998, and that was the machine that chip was, that project cost was US dollar 2,50,000 US dollar. Okay. And also DES is having some other problem with the like some non-generic attack like differential. Those we will cover later stage. Differential cryptanalysis, linear cryptanalysis. So for that, the TDS was not popular, because all the TDS overcome that problem of brute force attack or exhaustive search attack, but it has a drawback of it is basically it is using the same DES functionality. So if we have used the same functionality, then there is a then we can mount those attack like non-linear attack, linear attack, differential attack, all these things. Okay, so that is the problem. But so TDS was not successful in that sense. So then people start up thinking, because DS was standard. DS was standard, and people used to work in blindly. So now they came to know the DS is broke. So now they are trying to find a new standard. So in IST, they wanted to help in creation of new standard. So we need to have a new block cipher which we can trust for. So DES is no more trustable. It is no more secure. Okay. So so we have already tried with the DES, the triple DES, but that will not work. Then people decided to go for a brand new one. So brand new algorithm was required to resist all these attacks. So for that we need to keep that in mind that okay, it should have a sufficient size of key, and it should able to overcome all the existing non-generic attack. So those things should be considered when we are designing this cipher. So that time many people are working on this area. So they NIST, instead of designing by themselves, they open competitions. So instead of designing or helping to design the cipher, what NIST did instead, they set up a contest, open competition, globally, worldwide, which anyone in this world could take participate. And that time many PhD student was working on this cryptography, so they thought, okay, there is a golden chance to become a hero. Okay, so they start designing their dream block cipher. So, so the contest was announced in 1997, and the idea was to get a block cipher which is the best among all the submissions. So, and that they are going to put that block cipher to be standard, and the standard name they planned for Advanced Encryption Standard, AES. Okay, so idea was to develop a new encryption algorithm that would use for protecting sensitive because block cipher is fantastic. It is, if we have bulk encryption, we can just break it into blocks and then we can do the encryption on that. Okay, but the cipher had to meet lot of requirement and whole design has to be fully documented. Unlike DES, DES was not fully documented because we know the AES, S box of DES. They have just given in a tabular form, in a matrix, 4 by 16 by 4 by 16 matrix. That's all in the table. The data is given, but where from this data is coming, who gave this data, I mean, or something like that. There is no algorithm is given. So this is not fully documented, DS. So if it is fully documented means there should be full algorithm for each of this functionality in the encryption or decryption process. Okay. So we need that. We need a fully document. So once the candidate algorithm had been submitted, several years scrutiny process was going on because that time it was open competition. So if I had that time, no, I was too young. Anyway, so that time if some people were working on that, so they design and they submit into that website, and that website is public, so anybody can see that. So if I was the person working in that time cryptography, so I just took a block cipher from their submission. I did the attack and I got a paper. So like that, if I got 5 paper, I will getting a PhD. That way, so there was a huge involvement from worldwide, and there was a many submissions in the first round. So after first round, 15 were accepted after first round. 15 algorithm, 15 block cipher. There are many submissions, more than 100 maybe. So among them, 15 was the, so among these 15 in the second round, this 15 also having some drawback. Not all are very much secure. So we are working hard to get a paper. Okay, attack this cipher. So those cipher who are weak can be attacked. So those are gone. So we did attack on the other cipher. So finally in the second round, in the second round, every year there was a conference, a workshop, a meeting. In the second year there was a 5 cipher was finalized. So and then but we need to choose one. We cannot make the 5. It is not a tie. We have to put one cipher to be the standard. Okay. So finally, among these five cipher name was Rindel is one of the cipher. This is the name of the cipher. Then Two Fish, RC6, Surfend, and Mars, I think. So 5 cipher was there. The algorithm was tested. Then NIST also tested this algorithm. and then finally the Rindel was the winner. The name of the cipher, the name of the block cipher is Rindel, and this was the winner. And till today, this is the standard. Till today, the Rindel is the advanced encryption standard. So this Rindel name came from the designer name. It was designed by two Belgian cryptographers, John Damian and Vincent Richman. So from their name, you can see Rindel name comes. This Rich RIZN, maybe N is here, DAEL, I don't know, maybe their girlfriend name or something like that. So this name comes after their name. So Rindel is our, still today it is our standard, and it was standardized in 2001. So remember, it went 3 years. So DS was broke in 1997, and then Rindel came into the picture in 2001. So Rindel is a block cipher. So we have to know Rindel, and that is our standard till today. So let me open the board. So I will use board a little bit. Okay, any question? Good. Okay, so we are talking about AES, Advanced Encryption Standard. And that is, the name of the block cipher is Rindel. So this is the block cipher. Still today it is the standard. So there is no attack on full AES, full Rindel. AES means Rindel basically. Okay, so it is a block cipher. So for block cipher, what we need to know? We need to know few things about the block cipher. We know block cipher is a kind of encryption algorithm which takes some input as a plain text, and the plain text is having some fixed length. For Rindel it is 128 bit, so it can encrypt 128 bit, and the key size is some variant of the 128 is one variant key size, and then we have ciphertext is obviously 128. And what else we need to know about the block cipher? Another parameter? Anybody? Do you remember the general structure of a block cipher?
So the key scheduling algorithm.
But for that, where we have to put this key scheduling algorithm for? Round keys. Those are round keys. So that means we need to know the number of rounds, right? How many rounds are there? Yeah. So it has number of rounds are having 3 versions. For this, it is 10 rounds. And if we have, we can have 12 rounds if the key is 196, or you can have 14 round if key is 256. So there are 3 versions of this. This is key. This is plain text. So there are 3 versions available in their documentation. So based on this size of the key and the key, so if the number of round is, so this is one version, number of round, and the key is number of round is 10 and the key is 128. This is another version. This is another version. So this version is called AES 128. This is based on the key size. Don't think about it is a block size. Block size is fixed. For all the cases, block size we have fixed of 128 bit. So only the key size is varying. And then we have AES, for this version we have AES 196, which is just the when the key size is 192 and the round is R, and this is AES 256. But among these we'll just consider. So all are secure so far. So which one we will choose basically? So since all are secure, so we will choose which one? Because this version AES is having R round, R the 10 round. If we have less round and give the same security, so better we will use this. So this is the most popular one so far. So mostly people use this version. So AES 128-bit. So even in the class also we will discuss this AES 128-bit. Okay. So that is the thing. One minute. Is this okay? Okay. So we talk about this thing AES. Our version of the AES is AES 128. It's not 128 is the block size. So it's basically the key size, and the number of round is fixed. So number of round is, so this version is having what is the block size? Block size is 128. So this is ciphertext, and the key size is 128 also. And we have how many rounds? We have F1, F2, F1. Sorry, F R is 10. So that is the thing. 1 minute. So that is the thing. Is this okay? Any question on that before we move to the details on this AES?
Clear, sir.
Yeah. So now what we need to know? We need to know a few things. We need to know the round function of AES. So each round function of AES consists of 4 operations. The operations are basically subbyte, shift row, mix column, and add round key. So these are 4 operations, and we have to individually know what are those. Okay. So those are operations where we take this 128-bit and we perform these operations, and so basically say we have an input over here. So we first say apply say subbyte. This is one operation. Input is 128-bit. We have to check how we perform this. Then we have this after subbyte. I think we have. Let me just check. We have shift or
Shift to, sir.
shift row and mix column and add round. Yes, thank you. Yeah, so shift row, and then we have mix column, and then we have add round key. So for adding round key, we need to have a round key. For every time when we use the add round key, we need to have a round key. So this is a typical one round AES, one round function. Okay, we just use the 4 operations. This operation you have to know, but for the time being, just take the names. We have 4 operations: sub byte, shift row, mix column, add round key. And whenever we are adding a round key, we need to have a round key, and that again will come from the key scheduling algorithm that is there. Because we have a secret key, from there we need to have a round key. Okay, is this okay? So this now we need to know the full round AES. This is one round. So this is some F, one round. But in the first round we have a extra add round key operations. So let me just give you the picture. Yes, so this picture you can see now. Is it visible to you?
Yes, sir.
Yeah, so this is AES encryption. So you have a plain text. Plain text is just put into the first add round key. So that is one extra operation in the first round. This is a part of the first round. And then we have followed by these 4 operations: sub byte, shift row, mix column, and add round key. And whenever, so we have in the first round we need 2 round keys. So those we will discuss where these 2 round keys are coming. Where the round keys are coming. That is coming from key scheduling algorithm. So this is first round, and the second round we continue like this. In the second round we have this again sub byte, shift row. So after this here we have same round 2. Round 2 is this extra add round key is not there from in round 2. Okay, so this will continue up to round 9. So in the 10th round we are not having this mixed column operation. I mean, why they did not consider, that is their wish. Maybe they thought that okay, even without mixing the column we can get the same security in the last round, something like that. But this is, we have to understand their design. So we need to learn first, and then we can criticize why is that, why is those. But first we need to get the design. So in the last round we have the same round function, except the one operation is missing, that is the mix column operation. Is this clear? And this each round key is coming from some key scheduling algorithm. I'll come to that. This is encryption. Similarly, we have picture for decryption, but forget about decryption now. We first concentrate on encryption. Okay, is this okay? Before we move to the individual.
Yes, sir.
Thank you. So let me go back to the board. Okay, so now we need to know all these details about this sub byte, shift row, mix column, and add round key. So for that, let me just take a plain text. So plain text is how many bits? X1, X2?
1 to 8.
1 to 8. So we want to take it into byte. 1 byte is 8 bits. So up to, say, if it is X1, X2, then otherwise if it is X0, then we have 8, otherwise 7. Then so this is 1 byte. Then next 8 bit is another byte. So this is capital X1, capital X2. How many bytes are there then?
16.
Yeah, X16. Now we define this, we store in a matrix. So how to store in a matrix? The way they did is X1, X2, X3, X4, X5, X6, X7, X8, these values basically. X9, X10, X11, x12, x13, x14, x15, x16. This is the matrix. So how we initialize this matrix? We take this plain text values and we store it into this. Each of this is a byte, 8-bit. So which is like this. Is this okay? This matrix is called state. So basically it is a state-wise operation. We every time we pass this state to this operation which we are going to discuss, sub byte, SIP row, mixed column, and it will give us the output. Okay, is the state is clear? So this state we can just denote by general symbol, say S00, S01, S02, S0. In the book it is written like this. So like matrix, how we define matrix? 0th row, 1th row, then the 2th row, like that. Then it is starting from 0, so it will end with this is okay. So this is we initialize this. These are the variable maybe we can think of. If we are implementing this, you take this variable and each of these variable can take 8-bit, and we are storing these values over this. So basically we initialize S00 as x1, this first 8-bit of the plain text, then S10 as x2, like this. So we put this, we initialize this variables, the state variable, like this. So it is initialized by this, and every time we are passing this state and we are operating, we are performing these operations. Okay, the first operation is, if you have any question you can stop me anytime. First operation is sub byte. Sub byte is basically S box. What is this S box? This S box is 8-bit to 8-bit. AES S box. We take 8-bit and it will give us 8-bit. Okay, if it is A0 to A7, we have B0 to B7. So suppose we have a S box. How this S box is coming? We'll discuss. AES S box is having a rich formulation for that. I mean, it's not like DES S box. It's well defined, and we do have an algorithm to get the values, and it use some finite field there. So that is okay. That we can just state now, and when we talk about the mathematical background, then we'll learn more. But anyway, suppose we have a S box, such S box. Then how will apply this S box on this state? Any idea? So we have a state over here. We have S00, S01, S02, S03, S10, S11, S12, S13, S20, S21, S22, S23, S30, S31, S32, S33. Now suppose we have a S box. So this is sub byte operation. Suppose we have a S box. Then how we'll apply the S box on this state to get a new state? And these are, say, initialized by some value. So it is initialized by the plain text, and after that we have having some operations. So eventually we are dealing with the state. This is the state. How the state will change? Any idea?
So on each element you have to apply the S box.
Yeah, that's the idea. So if this is pi function, this is 8-bit to 8-bit. So this is basically, we take a element and we apply S box. This will be S00 prime, say. We take this, we apply S box. So S01 prime. So basically we have, say, Sij. Sij is going to Sij prime, which is nothing but pi of Sij. Is this okay? Because each of this is a 8-bit, some binary 0-1 bit. So we take that and we apply this S box on that, and we take the output and we store, we replace that value with that old value, and that's it. That is the new state. This is the old state, and the state will be updated by this state, new state. Okay. Is this clear? The sub byte, but we need to know this S box. That will come later stage. Suppose I have given you this black box, which can take 8-bit input and which can give you 8-bit output. So that black box you can use like this, right?
Yes, sir.
So we take we take each of these element. Each of this element is 8-bit. We apply the S box on that. We apply S box on this. It will give us the pi s of S21 like that. So Sij, if we map, it is pi s of Sij. So this old state value will be replaced by the new value by the S box output of the corresponding input, corresponding corresponding byte. This is the S box operations. But we need to know the S box. We need to know this function. That we know. Okay, so this is one thing. The next one is next one was what? Cipro, na? Cipro, we have shifting the positions. So let me again go back to the slide. Otherwise, we can save some time to draw it. Yeah, so here is the, can you see the slide?
Yes, sir.
Yeah, so here is the picture what I have explained you. So we have these states and we are taking a particular, we are taking each of these, and suppose S box is given in a tabular form. It is not in tabular form, we do have an algorithm for that, but suppose it is given in the tabular form. Tabular form means x and z. So I'll just explain this one a little bit. So before Sept Pro, let me just explain this S box in a tabular form. If it is given in a tabular form. So S box is how many bits? It is a 4-bit to sorry, 8-bit to 8-bit. So 8-bit means hex bit is 4. So you can just take 2 hex bit. Hex means 0 to 15, but 15 we have F something. So X could be this, Y could be this, and WZ will be also this number 0 to 15. Okay. Now how we can get a table of this? We can have a we can have a table like this, basically matrix. So this is X and this is Y. So 0, 1, 2 up to 15, 0, 1, 2 up to 15, and these all these fields are basically WZ. All these fields. So this is 2, this is 1. So this will be some value, say A3 or something like that. So WZ, some values like that. So if we have given this in array, then we can do that table lookup. We can do that table array lookup, and we can fetch that value. So that was the picture which I have shown. But how these values are coming? We have the algorithm. We learned that. But since the picture came, yeah. So this is our table. So this is, anyway, they are putting this row number as X, Y as column number. That is the convention. You can use anyone. So what we do, we take a byte over here. So byte is X, Y. So we fetch the value X and Y. We go to that particular row and column, and then we go to that element, and that element is also written as that form xy, wz. So we just replace that by wz. That is the thing. Okay. So yeah. So this is the. So let me go to the. I'll come to all of details of this. So let me go to the shift row. This is basically the shift row operation. So shift row means this is the first row, I mean 0th row, this is the second row, the 1th row, 2th row, 3rd row. So first row remain unchanged, we are not doing anything on that. So we are not disturbing this row. We are mixing somewhere, so second row what we are doing, we are shifting one position. So you see here, so this will come here, this will go here, this will come here, and this is circular shift, and this 10 will go here. So you can easily check that this is circular shift. And then this one is S20, we have shifting 2 times. So if you shift 2 times, then S22 will come here, S22, then S23, and this is circular shift. Then S21 will go here, and this will be S21. There is a printing mistake over here. This will be S21 here. Okay, and this one is 3 times. Is this okay? This shift row operation? Any question on that? Okay, so shift row and subbyte is okay, but subbyte we need to know more about this S box. It is left. Now let us move to the this. And what about add round key? Add round key is very simple. We have round keys. Round keys are also 128 bit. All round keys are 128 bits. And we have the state sizes. State is also 128 bit. So add round keys is just basically bitwise XORing. So you just do the bitwise XORing. So you have two 128 bit numbers, 0-1 numbers. So you can do the bitwise XORing. That is the basically add round key. So our round keys is 128 bit. So how many round keys we need then for AES this version? Any idea? How many round keys we require?
10.
20.
10 is
12.
close. 12 is close.
Sir, 11, sir.
11. Why 11?
So in first round we are taking 2 times, sir, and
So first
one
round we are having one extra round key operation. Otherwise, it is every time we are taking one time, but in the first go we are taking one extra round key operation. So that's why it is 11. So 11 round keys we need from the secret key. What is the size of the secret key? Any idea? What is the size of the secret key shared between Alice and Bob while doing the
19.
secret key size? The key size. Any idea?
152, sir.
No, 122, 128. Key we have is 128, no? Because this is that version only. Okay, so can you move further for this? Which board you are seeing? Are you seeing the board or the slide?
There is slide.
So but I need to get a board over here. Okay, now I'll describe the S box. Okay, so here we'll do a little bit of maths over here, but that is okay. That is, we can understand. Let us try that. Okay, so AES S box is how many bits? 8-bit input, 8-bit output. So 8-bit we can write as A1, A0, A1, A2, A3, then A4, A5, A6, A7. And then we should get the B0, B1 up to B7. Now this is 8 bits. So 8 bits, can you form a polynomial out of it? How to form a polynomial? So Px is nothing but how to form a polynomial? A0 plus
Plus A1
A1x
X.
plus A2x square. So what is the degree of this polynomial? It's a 7-degree polynomial. So these AIs are basically 0 ones. These are binary. We are dealing with the binary numbers. So AIs are 0 ones. So the input we can think of a polynomial of 7 degree. So the 7-degree polynomial we want to bring from some. Now we want to define some what is called field, Galba field. So for that, let me take some polynomial x to the 8, 4, 3, 1. 8, 4, 3, 1. So x to the power 8 plus x to the power 4 plus x cube plus x plus 1. This is a 8-degree polynomial. 8-degree polynomial. Are you familiar with Z2x? A polynomial of any degree where coefficients are coming from 0, 1. What is Z2x? Z2x is any polynomial, say 1 plus x to the power 90 plus x to the power 2020 plus x to the power 50. This is a Z2x. Why? Because coefficients are 0, 1. Here we have 1 plus 0 into x plus 0 into x square dot like this. So any polynomial can be written as summation of some di's x to the power I is equal to 0 to infinity in the if we. So this is a infinite size. So this is not a finite set, this polynomial set where di's are coming from
Z2.
Z2. This is Z0, 1. That's why it is Z2x. So this is a set of all possible polynomial we can think of where coefficients are coming from 0, Z2. Now this is an infinite set, like our integer is infinite. Now somehow we want to make it finite because our computer can understand finite business. So to do that, we know one technique. We know that mod will help us. So we take a polynomial, say that polynomial of 8 degree, x4 or what? Yeah, x4, x cube, x plus 1. This is a irreducible polynomial basically. Irreducible. So irreducible polynomial means we cannot reduce further. This is a 8-degree irreducible polynomial. There may be another 8. There are many 8-degree irreducible. We take one of them. That is a px. Now, if you take any polynomial from Z2, say qx, you take any arbitrary polynomial from Z2. Z2x. Now if we want to divide that polynomial with this, then what will be the remainder? Remainder will be how much degree? Maximum. You understand? We take a polynomial. Say we are taking say qx is say 1 plus x square plus x cube plus dot 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 plus sorry dot 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 I will not use here, plus x to the power 9 plus x to the power 21, like that. This is one example. Suppose this is a polynomial of 21 degree. Any degree you take, doesn't matter. Now when you take mod of this polynomial, what does it mean? That means this is a polynomial division. So we divide this polynomial 1 plus x square plus x cube plus dot 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 plus x to the power 21 with this our x to the power 8 plus x to the power 4 plus x cube plus 1. If you do that, then we are having here some say wx, and we are having here rx. So remainder polynomial. So basically qx will be written as
7 degree.
7 degree maximum. So wx into px plus rx. This is called quotient and this is called remainder. This we know, na? Anyway,
Yes,
we will
sir.
discuss this in more details. And so this is the remainder, polynomial division. So remainder, as you said, remainder will be maximum 7 degree. So 7 degree means what? 7 degree means it will be either this form d0 plus d1x plus d2x square dot 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 d7 x to the power 7. Okay. Now if you take this px to be irreducible polynomial of 8 degree, then eventually if you take all possible polynomial z2x mod this px x to the power 8 plus one example, this px is another we can take. This will give us all possible 7 degree
Polynomials.
Okay, and this is a we discuss the field. This will form a field under two operation, plus and multiplication, polynomial plus and multiplication under mod of this polynomial. When you multiply two polynomial, then we take the mod of that. Again, it will be 7 degree. It will come here. If we add two polynomial, again we take the mod. For addition, we may not need to take the mod because addition will not increase the value of the degree. But when we multiply two polynomial from here, so this will form a field. And what is the size of this field? And what is the size of this set? This is a 7 degree polynomial. All possible 7 degree polynomial will come. What is the cardinality of this? 2 to the
2
power
power
8.
8.
Super eight.
So this is called finite field basically because the size is finite, and this is also having a name Galois field. So we'll take this field for our constructing our S box. Okay, that anyway will continue tomorrow. Is this okay? So this is little bit of field. You just bear with me. We'll discuss in more details. But since I wanted to finish the block cipher before we move to the mathematical things, because we need to know more mathematics like sorry, some number theory we need to discuss. Anyway, we'll do it in the next class. Okay. Sorry. So,
Yes, sir.